This video is on fossil fuel and nuclear power stations. It is the second video on topic 8 of IB Physics. This is part of the core material, so it's the same for SL and HL students. Take a moment and read the success criteria that we will cover in this video. Pause it if you need to. So burning coal right here will cause the water inside the tubes to turn into steam. That pressurized steam is going to then move through, causing the turbines to turn, and the generator will rotate in a magnetic field, creating electricity by electromagnetic induction. Now there are several different sections to this plant. Notice that when the coal comes in here and burns, it's going to go out through this tall, thin stack. That means that it's separate from the water that actually will go through these tubes to the turbine generator and back again. In a different circuit, water here from the river or nearby lake typically is going to go up to the generator, and it's going to cause that steam to turn back into liquid water so that it can return again and be heated and continuously move through our power plant. This water here will typically go back to a large, thick stack. Those large towers at the power station, they're actually the cooling towers I'm talking about. So the gases you see from the top of them are actually condensation and not the carbon dioxide or sulfur dioxide that contribute to climate change or acid rain. Those are the ones that are coming out this stack right here. Now, the overall efficiency of a coal power plant is around 40%. Not all the chemical energy in the coal gets converted to electricity. There might not have been complete combustion of the coal, and so the exhaust gases that are leaving out this stack here, they might still have some chemical energy, but they're also going to take with them some heat, as well as there's some heat given out when the turbine condenses. There's also some friction components in the turbine and the generator, which will also reduce its efficiency. For each type of generating electricity or power, you really need to know some advantages or disadvantages. Make sure you have a couple of each type that you're able to use and talk about. Pause here, or you can also find these in your textbook as well. One possible energy transformation for this particular power plant could be solar energy was used and changed into chemical energy in the plant through photosynthesis. Then, over time, that chemical energy was turned into the fossil fuel. In this case, could be coal, could be oil, natural gas. Then, with combustion, thermal energy was released in the power plant. That caused kinetic energy of the turbine, and finally then to electrical energy. We can do lots of these different ideas of energy transformations. Sometimes they'll get you to start perhaps at the beginning with the solar energy, or other times they'll be expecting you to start where the chemical energy contained inside the fuel. Let's do a question. A power plant produces electricity by burning coal. The thermal energy produced is used as input to a steam engine, which makes the turbine turn, producing electricity. The plant has a power output of 400 megawatts and operates at an overall efficiency of 35%. Part A. Calculate the rate at which thermal energy is provided by the burning coal. Okay, so let's start with our equation for efficiency. Now, one thing I want to point out, this question says the rate at which thermal energy is being provided. Rate of energy, that would be the power. We can use this efficiency for useful output power over total input power, or we could be using it for energy. So let's put in our values. The efficiency of 35%, 0.35, will be 400 megawatts over what we're looking for. Let's call it X. doing the math, you should get 1.14 times 10 to the power 3 megawatts. Okay, so let's go on to part B. Calculate the rate at which coal is burned. Use a coal-specific energy of 30 megajoules per kilogram. Now, part of this is really looking at the units that you need to have in your final answer. Calculate the rate at which coal is burned. Well, that should be having units of kilograms per second. So let's take the information we have so far. We have 1.14 times 10 to the power 3 megawatts of energy. Let's change those units for just a second though. 1.14 times 10 to the 3 megajoules per second. If I divide that by the specific energy, 30 megajoules per kilogram, I'm going to get 38, and look what happens to those units. Megajoules per second divided by megajoules per kilogram. Remember, invert and multiply gives me units of kilogram per second as required. And finally, part C. The thermal energy discarded by the power plant is removed by the water. The temperature of the water must not increase by more than 5 degrees Celsius. Calculate the rate at which water must flow. Remember, units, rate at which the water must flow. That's going to be in kilograms per second again. Well, we're heating up water again, so let's start with our equation that we know we're going to use for heating up water. Q equals mc delta T. And we're doing rates here, so it's going to be per time and per time. And there's that mass per kilograms that we know we're going to look for. Kilograms per second we know we're going to look for. But what is that Q per T again? That's energy per time, rate of energy. Right, that's power. So how much of the power is actually going to go into the heating the water? Well, we have a total of 1140 megawatts in total, but we have some going to the actual production of electricity. So we know that from the question is 400. So what must be left over is the water, the power that's going to heat up the water. Let's put the rest of our values in here. Now the mass per time, that's what we're going to be looking for. C for water, 4,200 joules per kilogram per Kelvin, or Celsius. Remember, this is a change in temperature, so it doesn't matter which one. You don't have to know this number. It's not in our data booklet, so somehow they'll either have to give it to you or have a way for you to be able to calculate it. But it's not a required memorization. And then the change in temperature is only allowed to be 5. So if I move this around, we're going to have m over t will be our 1,140 minus 400 all over 4200 times 5. And if we put that all in our calculator, we should get around 3.5 times 10 to the power 4 kilograms per second. Again, these questions, there's not a set, oh, I have to use this equation. You're using information from previous topics, putting them together. Pay attention to the wording. The rate of something always is a clue, which means I need something per time. Be a master physicist. Make your own equations.